7.8, Logistic Growth and Newton's Law of Cooling. There are 4 types of differential equations for which we're responsible in Calc BC. The first 2 are type 1, position, velocity, and acceleration, which if you started with your dv dt is equal to negative g, and you separated that, I'd multiply by dt on both sides, integrate, that would give us v equals negative gt plus c. So that's how you get your solution there for your velocity. Type 2 is exponential, and to show you how that one works, dy dt equals k times y. So we want everything that has a y on the left, and we're going to keep that k on the right with the dt. We're going to multiply by dt and then integrate both sides. Natural log of the absolute value of y is equal to k times t plus c. And now you're going to take both to the power of e, and this becomes y equals, and we're going to break this up into e to the kt times e to the c, and we're going to let a equal e to the c, and actually if this was an absolute value, we could say let a equal plus or minus, and then we could have our y equals a times e to the kt. And that would be your solution here. They used C right here. I used A. Okay, so either way. And then type 3 is the logistic differential equation. So that's what we're going to focus on today, the logistic one. So example number 1. They've given us dp dt equals kp times the quantity 1 minus p divided by L. K and L are positive constants, and we're going to solve this. So we want everything that has a p in it to be on the left-hand side. So I'm just going to divide both sides by p times 1 minus p over L and leave that dp there. The only thing that stays here is k. And integrate. Now we have to do some a little bit of side work here. I'm just going to say side, because our 1 over p times 1 minus p over L is equivalent to, imagine making that 1 L over L. So this is 1 over p times L minus p all over L. And then simplifying this complex fraction is going to give us L over P times L minus P. And then using our partial fractions, we would say, again, probably side work. I want to set this equal to something, but over here, just to show partial fractions, we're going to do A over P plus B over L minus P is what we want this to become, okay? And to do that, our A times L minus P plus our B times P has to equal L. And so if we let P equal L, then we're going to get 0 for A, and this is going to give us L times B equals L, so our B is 1. And if we let P equal to 0, then our B turns to 0, and this is L times A equals L, and our A is 1. So that gives us if by using partial fractions, that gives us that this right here is equal to 1 over p plus 1 over L minus p. So this is going to be the integration of 1 over p plus 1 over, sorry about that, I just wrote L, 1 over L minus p dp is equal to integral k dt. So again, this is just really hard to find the place to write, but I think I'm going to scoot this over, and we'll separate that 1 over p dp plus the integral of 1 over L minus p dp is equal to the integral of k dt. I was able to fit this all on my paper. It's just writing on this iPad, I just can't fit it. Now, notice that when I integrate, the first one's easy, ln of the absolute value of p. The second one, though, notice that if you take the derivative with respect to p, it's -1. So this is going to become negative ln absolute value of L minus p. And this becomes kt plus c. So I put plus a minus, but it's really just going to be minus. So we've got our ln absolute value of p minus ln absolute value of L minus p equals kt plus c. And then putting those together, ln of p divided by L minus p is equal to kt plus c. Now, what I want to do is I want the monomial to be in the denominator. So I'm going to negate this, and that flips this around. But then I have to negate this, and I'm going to go ahead and negate my c. Even though the constant typically, it doesn't really matter, but I'm just going to do it that way. Now we're going to take, sorry. When I negate that, it flips it. I don't need that negative sign. Sorry about that, but I actually negated it. So now, we're going to take e to the power. And this becomes absolute value of L minus p over p equals e to the negative kt times e to the negative c. And we're going to let a equal e to the negative c. So our L minus p over p is equal to a times e to the negative kt. And so now we're going to split these up. L over p minus 1 equals a times e to the negative kt. And then we'll add 1 to both sides. And solve for p. And that is our solution to that original differential equation. And it does end up being a logistic equation. Okay, so I'm going to move this back so we can go back here to see this note up here. And hopefully you noticed that the procedure for everything that we just did is right here, and it's basically everything that we just did. We separated the variables, we integrated both sides, we used partial fractions to rewrite the left-hand side, we found the antiderivative of each side, we multiplied both sides by -1, which flipped our P over L minus P to L minus P over P. And then we simplified exponentiated, which e to the power. We let a equal, and I forgot my plus or minus there. I should have put plus or minus there on my e to the negative c, and we solve for y. But I want to focus on that note. It says the parameter L represents the limiting value. Okay, so L is your limiting value. That's what it'll approach but not touch. The parameter K represents the relative growth rate when P is small relative to L. And the parameter A depends on P sub 0. So this right here is important. And really just all of those things that talk about what P, L, and K are. Okay, so let's go to our next page. So we have carrying capacity L is the maximum population. That the environment is capable of sustaining. And as P goes to 0, your dP dt goes to K times P. As P goes to L, your dP dt goes to 0. And the graph of the function P is called the logistic curve. And in logistic growth, the population grows the fastest when the population is half the carrying capacity. So we have our carrying capacity here for this one. That's going to be your y equals 4. That's what it looks like anyway. Notice that your point of inflection is where there is a maximum slope. So that's your greatest derivative. And notice that we have concave up, and then after that point of inflection, it turns to concave down. Also notice that the function of, all along here, before it hits that point of inflection, is growing exponentially. And then it starts to slow down after that. But it looks just like an exponential curve until the point of inflection. And so max value of dP dt P equals L divided by 2. So to find the time of the maximum rate of change, we do 1 over K times the natural log of A. That's the relationship to find the t value of that point of inflection. The slopes are small near P equals 0 and P equals L. They're very flat, okay? They are steepest around the point of inflection. And that is at L divided by 2. What happens if P is greater than L? Slopes are negative. Population decreases. Okay. Example number 2. So a population of coyotes in a wildlife preserve is modeled by a logistic function. The preserve can support no more than 100 coyotes on the property. Write the differential equation with k equal 0.1, where t is measured in years. So our dp/dt is equal to, it told us that it was, k was 0.1 times p times 1 minus p divided by our maximum of 100. And so if we look at that and we do the same thing that we did making that 100 divided by 100, it's the same thing as 0.1 p equals 100 minus p over 100, or times 100 minus p over 100. And then if we combine that 0.1 divided by 100 here on the outside, I'm just going to circle it like this. If we make that, if we make that an actual number, that is going to be 0.001 p times 100 minus p. And so that's a good dp/dt that they're asking for, right? The differential equation with k equal to 0.1. There it is. So the slope field is shown at right. Where does the horizontal asymptote appear to occur? And so to me, it looks like that horizontal asymptote is right here at 100. So y equals 100. And that is your carrying capacity. And what happens if the initial population is above this asymptote? That means the population is in decline. It is overpopulated. For the preserve. And if the preserve initially begins with 20 coyotes, sketch a graph of P of t on the slope field. Okay, so at t equals 0, your population would be 20, so I'll put a dot there. And let's think about this. If our initial population is 20, we said that we can find our A by taking 100 minus 20 divided by 20. So our A is 4. And so our equation is going to be P of t equals, here's our initial population, over 1 plus 4e to the negative 0.1 t, because our k was 0.1 and this was negative kt. And so this will allow us to put this in our calculator, and we can get a couple more points. I have the point 13.863, comma 50, because that is our point of inflection. So it's about right there. 13.863, comma 50. And then I also have the point 27.726, comma 80. And that one looks like it's about right there. So something like that. And again, this was a calculator problem, so you can get those points by using your calculator. I put 50 into my y. I did, like my y1 was this, my y2 was 50, and I found the 13.863, and then I did 80. Okay. Found that point of inflection. All right, so now letter E, find the general solution and the particular solution of the differential equation such that P of 0 is 20. So for that one, we are, just for a change of pace, I'm going to use pink here. We're going to start with our dp dt is equal to 0.1 p times 1 minus p over 100. And we're going to split it up so that everything with a p is on one side, everything that doesn't have a p on the other. Usually we keep that constant over on the right-hand side. All right, so now we're going to work on simplifying this like we did before. So we would, make that 1 over p times 100 minus p over 100. And then we would make that simplify our complex fraction and use our partial fractions. So we know that a times p plus b times 100 minus p is what we're looking to make this right here. And so we have to take a times 100 minus p plus b times p, and it's going to equal our 100. This right here, numerator. Because we're taking this and we're making it into that. So now, if p equals 100, then we have 100b equals 100, and our b is 1. If p equals 0, then we have 100a equals 100, and our a is 1. So this becomes 1 over p plus 1 over 100 minus p dp. And so now we'll split these up. Integral of 1 over p dp plus integral of 1 over 100 minus p dp equals integral of 0.1 dt. So natural log of the absolute value of p, and remember minus, because when you take the derivative here you get -1, natural log of the absolute value of 100 minus p equals 0.1 t plus c. And then this becomes ln, absolute value of p over 100 minus p equals 0.1 t plus c. We're going to continue it over here. Negative, so that we can get the monomial in the denominator. And then e to the power on both sides. And I think you guys will be okay if I just do, actually let me do it in black, e to the power, e to the power. And then this becomes 100 minus p over p equals e to the negative 0.1 t times e to the negative c. We're going to let a equal, this is absolute value, we can say plus or minus e to the negative c. And then we would have 100 over p minus 1 equals a times e to the negative 0.1 t. 100 divided by p equals 1 plus a to the, times e to the negative 0.1 t. and then solving for P. Okay, so that's without a specific starting point, like a specific initial population. If we put that initial population at times 0, there were 20 coyotes. If we put that in, 20 equals 100 divided by 1 plus A times e to the 0. So basically you're going to end up multiplying by 1 plus A on both sides and dividing by 20 on both sides, and your 1 plus A is 5, and then subtract 1 from both sides, your A is 4. So this is, basically separating it and figuring this all out. We've got this value with this equation, and we put that all together, and that's our solution with that would be our particular solution, because they've given us that starting point. So up here, our final answer, I'll put in blue. We've got as a final answer of P equals 100 over 1 plus 4e to the negative 0.1 t. That's our particular solution with that value. Okay, so when will the coyote population reach 80? So at that point, you would say we're going to set 80 equal to the 100 over 1 plus 4e to the negative 0.1 t. And multiply by that on both sides. Divide by 80. This, I'm showing you how to do this algebraically. You might have to do that on the AP exam. 5/4 and subtract 1 from both sides. And then divide by 4, which is multiplication by 1/4. And then natural log. Now, when we're doing natural log, we know we can bring that negative 0.1 t down, times ln of e is 1, and also this is ln 1 minus ln 16. ln 1 is 0. So this becomes negative 0.1 t equals negative ln of 16 divided by negative 0.1. And you would get your t value of 27.726 years for our F. And like I said, I was able to fit this in when on my paper, but when I'm doing it here, it just doesn't seem to fit. I can just change colors. So letter G, when is the coyote population growing the fastest? And for that, you would say P equals L over 2. So P is equal to 100 over 2. So that would be at P equals 50. And if you wanted the t value, you could say, oh, I know that's 1 over k times the natural log of a. So that would be 1 over 0.1 times the natural log of 4. And that would give you your 13.863 years. And those are the two formulas that we got from above. And then find the limit as t goes to infinity of p of t. Well, that's easy. That's 100. That's that horizontal asymptote, or your carrying capacity. Okay, so that's the logistic differential equation. The last one that we need to look at is the Newton's law of cooling equation. And so This one is a little bit different because we're used to using that other formula that we used in pre-calculus, but we're not using that. We're using a differential equation. Remember that your B up here, because this is your form, and your B is the temperature of the surrounding medium, whatever that is. It might be, you put it in the refrigerator, so it'd be the temperature of the refrigerator, or you took it out of the oven, so it'd be the temperature of the room. So that is your B up here. And so, example number 3, you bought your favorite frozen coffee treat on the way to school at the drive-through window of Starbeams. Your car is always kept at a constant 65 degrees Fahrenheit. So you're taking that coffee that's a certain temperature and you're putting it in that surrounding medium of your car, which is 65 degrees Fahrenheit. So that is your B. Traffic was terrible and you spent 10 minutes getting to school. The drink warmed to 35 degrees because you checked it with your temperature probe at the red light. Then 2 students had a rear-end collision and another 10 minutes passed trying to get into the school parking lot. You checked your drink again. It warmed to 50 degrees. For this one, you've got 2 points basically that you know. They told you after the first 10 minutes it was 35 degrees Fahrenheit, and then 10 more minutes, so that would be after 20 minutes, it was 50 degrees Fahrenheit. I don't really like the way it was worded. There were a couple of places where I thought the wording was weird, but this is what they were trying to say. So if I know that my differential equation, dy dt, for Newton's law of cooling is some k times y minus whatever my temperature of my surrounding medium is, this is my initial differential equation based on this form right here, okay? I don't know k. We're gonna, split this up. We want everything with a y on one side, so I'm gonna divide by y minus 65 and keep my dy here. I'm gonna multiply by dt. I'm gonna integrate, which is what we've been doing when we separate. And so this is going to be the natural log of the absolute value of y minus 65 is equal to kt plus c. And take e to the power on both sides. So e to the power. And absolute value of y minus 65 is equal to e to the kt times e to the c. We're going to let a equal e to the c. Or I guess plus or minus, right? Because we're going to take off that absolute value sign. A times e to the kt is what my y minus 65 is equal. And then our y becomes a times e to the kt plus 65. So this is your general solution. We can find a particular solution by putting in these values. Okay, so remember all of these values are going to be little t comma big T values, which actually we're using y, little t comma y, sorry. Let's just make that y since that is a y. So little t comma y. All right, so now we're going to take our 2 points. We have a y value of 35 is equal to a times e to the 10k plus 65. And we also know that 50 equals a times e to the 20k plus 65. So these are our 2 equations. And we actually have 2 unknowns, a and k, and we can use substitution or elimination to solve them. One thing I did was I subtracted 65 from both sides of both of these equations before I did anything else, and I got negative 30 is equal to a times e to the 10k, and I got negative 15 is equal to a times e to the 20k. So there's my new equations. And then I said that, oh, well, if I negative 30, I solved them both for a. I just divided by e to the 10k on the first one. And basically, I'm just saying a equals a right here, right? This a is equal to this a. And then I divided by e to the 20k. And so this a, I don't like where I put that, a equals a. Sorry about that. But basically, that's what I was saying here. Because I solved for a. I divided by e to the 10k. And then I solved for a here. I divided by e to the 20k, and then I said, oh, well, these are the same a equals a. And then I cross multiplied. So now, if I divide by negative 15 on both sides, I get 2e to the 20k equals e to the 10k. Oops, sorry. And then, if I divide by e to the 20k on both sides, I get 2 is equal to e to the negative 10k. And I take natural log of both sides. I get natural log of 2 is equal to negative 10k. Because I bring that down in front, times natural log of e, natural log of e is 1. Divide by negative 10 on both sides, my k, ln 2 over negative 10. And that gives us negative 0.0693 for k. But I'm going to tell you that the best thing to do, even though that gives you kind of a rough idea of what k is, the best thing to do is leave your k this exact value, because you're going to be answering more questions, and that's going to give you a better exact value. Okay, so what do we have now? I know this is so long, I'm sorry. I did get to, like I said, I fit this all on my paper, so I'm hoping that you'll be able to fit this all on your paper. You're just going to have to kind of write small. So now what we have here is we have this. So that leads us to this. And now we're going to put one of our values in to find a. So I just want to put a t comma y in to find a. And so I chose the one where it was 10 comma 35. So 35 equals a times e to the negative ln 2 over 10 times 10 plus 65. So those 10s cancel. When I subtract 65, I get negative 30 equals a times e to the negative ln 2. And that's easy because e to the negative ln 2 is going to be 1/2. So I got a times 1/2 equals negative 30, multiplied by 2 on both sides. My a is negative 60. So last thing to do, y equals negative 60, e to the negative ln 2 over 10 t plus 65. And what they were asking, back up here, what was the frozen coffee's original temperature? So we had to separate and do all this stuff to get to our equation here. And now we want to find out what y of 0 was. Negative 60 e to the 0 plus 65. So it's going to be negative 60 plus 65, 5 degrees Fahrenheit was the original temperature. That was our y sub 0. So that's the answer to part A. Okay, and when you turn your page, part B, when would the drink reach a temperature of 63 degrees Fahrenheit? So that one, you would use your y equals negative 60 e to the negative ln 2 over 10 t plus 65, and you're looking to see when your y is going to be 63. Now be careful, the biggest mistake I see is that kids want to do something with that negative 60 before they subtract 65. You got to get rid of this one first. So you've got your negative 2 is equal to negative 60 e to the negative ln 2 divided by 10t. Now you can divide by negative 60. 1/30 is equal to e to the negative ln 2 divided by 10t. And natural log of both sides. And remember, this is ln1 minus ln30. And ln1 is 0. So that's going to give you negative ln30 on that side. This one, your negative ln2 divided by 10t comes down times your ln e. And of course that goes to 1. So this is equal to negative ln2 divided by 10t. Multiply by 10 on both sides, and divide by negative ln2. So it's going to be 63 degrees at, if you put this in your calculator, 49.069 minutes later. And you could put an approximation on that because we had to round it. So after approximately 49 minutes, the drink would be 63 degrees Fahrenheit. After approximately 49 minutes, the drink would be 63 degrees Fahrenheit. And then part C, what would the temperature of the drink be after 1 hour? So again, starting with your y equals negative 60 e to the negative ln 2 divided by 10t plus 65. You want to be solving for y of, now remember, t is in minutes, so you would be solving for y of 60. Do not solve for y of 1, because that would have just been 1 minute, and they wanted 1 hour. And so, oops, I went and forgot to put my 60 in there, sorry. So divide by 10, negative 60 e to the negative 6 ln 2 plus 65. And if you put that in your calculator, you should get 64.0625 degrees Fahrenheit. So after 1 hour, it's going to be 64 degrees Fahrenheit. Okay. I know that was messy. There's lots of writing on this one, so very sorry.